Welcome back to the deep dive. Today we're tackling, well, a truly massive cold case from our planet's history.
Yeah, it's a big one. We're talking about Earth's oxygen.
Specifically, why it took so incredibly long for our atmosphere to actually get oxygenated. We've looked at the sources, and there's this huge puzzle.
A nearly billion-year gap, isn't it?
Exactly, between life first figuring out how to make oxygen, photosynthesis.
Which cyanobacteria did pretty early on.
Right. And then the atmosphere actually filling up with enough oxygen to support complex life later on. It just doesn't add up, timeline-wise.
Uh-huh. That whole period, or rather the event that ended it, the Great Oxidation Event, the GOE, it's fundamental.
So our mission today is to dig into this delay. We're going beyond the usual suspects, things like volcanoes or other microbes eating the oxygen.
Would have been the main theories for a long time.
Yeah, and we're focusing on what the latest research points to. Two, kind of surprising chemical throttles, nickel and urea.
It sounds almost too simple, doesn't it? Trace compounds. But yeah, that GOE happening roughly 2.1 to 2.4 billion years ago,
Right.
it basically terraformed Earth for us.
But the timing has always been the issue. Why the wait?
It's been a real head-scratcher for geologists, for biologists, for a very long time.
Okay, so let's lay out this anomaly clearly for you listening. You have these microbes, cyanobacteria,
Tiny little powerhouses.
evolving the ability to produce oxygen hundreds of millions of years before the GOE really gets
The
going.
machinery was there. The potential was there.
But as the sources confirm, atmospheric oxygen just stayed very low for an extended time. Like the planet was stuck in neutral.
For a huge chunk of geological time, something was definitely putting the brakes on.
So what were the previous ideas? You mentioned volcanoes.
Right, so scientists thought maybe volcanic gases were reacting with the oxygen, pulling it out of the air as fast as it was made.
Or maybe other chemical reactions in the oceans? Sinks, they call them.
Yeah, chemical sinks, or even other microbes that used oxygen, sort of breathing it in before it could build up.
Okay, those make sense on a planetary scale, but
Yeah.
why didn't they fully explain that massive, stable delay?
Well, they probably played a part, but matching the scale and the sheer length of that low oxygen period, a billion years is a long time for things to stay suppressed. None of the models quite nailed it down perfectly.
Which brings us to this newer research from Okayama University, led by Dr. Dylan Ratniak.
Yes, and their approach is quite different. They're saying, maybe we should look smaller, much smaller.
At trace elements, at these specific compounds, nickel and urea.
Exactly. Suggesting these weren't just passive bystanders, but active controllers of life's pace.
Okay, I'm still trying to wrap my head around this. We're talking about tiny amounts of stuff, right? How could nickel and urea possibly hold back a planet-wide transformation, override volcanoes and everything else?
Well, maybe override isn't the right word. It's more like they controlled the engine directly. The idea is they regulated how fast the cyanobacteria could grow and multiply.
Ah, so limiting the source of the oxygen.
Precisely. If the bacterial populations couldn't bloom properly, they couldn't produce oxygen on a massive, sustained scale needed to fill the atmosphere. These compounds acted like inhibitors, directly on the microbes.
There's a quote here from Dr. Ratniak about this relationship. It sounds complex.
It is, he says. Nickel have a complex yet fascinating relationship with urea regarding its formation as well as its biological consumption,
Okay.
while the availability of these at lower concentrations can lead to the proliferation of cyanobacteria.
Right, so that last part is key. It's all about the concentration levels.
Exactly, it's dose dependent.
So the thinking is, back in the early Archean oceans, there was maybe a lot more of this stuff around. High concentrations.
That's the hypothesis. Especially nickel, perhaps weathered from fresh volcanic rocks before extensive land weathering processes kicked in.
And high levels acted like, well, like a poison, or at least a stressor.
A stressor, yeah. Enough to keep the cyanobacteria populations in check, preventing those massive blooms needed for large-scale oxygenation.
So the critical moment wasn't life inventing photosynthesis.
No, that happened way earlier.
It was when the levels of these inhibitors started to drop.
That's the new model. As nickel concentrations gradually fell over geological time, maybe due to changes in volcanism, maybe different rock weathering,
And urea levels maybe stabilized or found a balance.
then the chemical handbrake was released. Suddenly, the cyanobacteria were free to really take off globally.
And that unleashed the flood of oxygen that became the GOE.
That's the idea, a slow chemical change enabling a massive biological boom.
Okay, it's an elegant idea, But how do you even test something like that? You can't exactly visit the Archean Ocean.
No, you have to build it in the lab, essentially. The research team designed a really clever two-part experiment.
Right, to simulate those ancient conditions, what was the first part?
First, they had to show that urea could even exist back then. Urea is an organic compound, important for life, uses nitrogen.
But could it form naturally, without complex life already widespread, especially with the intense UV radiation hitting the early Earth? No ozone layer back then.
Exactly. So phase one, they took simple chemicals thought to be common in early oceans, ammonium, cyanide, some iron compounds.
Stuff that would have been around?
Yeah. And they mixed them together and blasted them with UVC light, the kind of intense UV that would have reached the surface back then.
And did it work? Did they make urea?
They did. It confirmed that urea could form abiotically, non-biologically under those conditions. So
Yeah.
step one, the potential chemical throttle, urea, was definitely plausible. It could have been present.
Okay, so the inhibitor could have been there. Now, phase two must have been about seeing how it affected the actual life forms, right? The cyanobacteria.
Spot on. Phase two was the microbial growth test. They took a specific species of cyanobacteria, Senechococcus PCC 7002, known to be pretty robust.
And grew it under different conditions.
Yes. They set up cultures mimicking day-night cycles with alternating light and dark periods. And crucially, they varied the amounts of nickel and urea added to the growth medium.
From low to high concentrations, I assume.
Exactly.
Yeah.
And they measured the growth carefully using things like optical density, which tells you how much stuff is growing, and chlorophyll content, which relates to photosynthetic activity.
So they could map out precisely how nickel and urea affected growth rates. And what did they find? Did it match the hypothesis?
It really did. The results were pretty clear. Depending on the concentration, nickel and urea could either help the microbes grow or strongly inhibit them.
So low levels might be okay, even beneficial perhaps.
Right, trace amounts of metals can be nutrients. But high concentrations, they slam the brakes on population growth.
Wow. So the experiments basically proved the mechanism. High nickel and urea could have absolutely kept the cyanobacteria suppressed for a long, long time.
It provides strong experimental backing for the whole idea. The rise of oxygen wasn't just about life evolving the trick. It was about the environment slowly becoming less toxic or less inhibitory for that life to flourish on a global scale.
The planet was essentially waiting for its own chemical fever to break, waiting for the inhibitors to decline.
That's a good way to put it. So this synthesizes into a new model for the Great Oxidation Event. Early Archean, high nickel urea keeps a lid on things. Then a gradual decrease in nickel, maybe stabilization of urea.
Removes those barriers and boom, GOE finally kicks off.
Igniting that massive oxygen release that changed everything.
It really does reframe how you think about early Earth, doesn't it? We tend to focus on the big dramatic stuff, volcanoes, asteroids, continents moving.
Yeah, the geological heavy hitters.
But this suggests that subtle, almost invisible changes in trace chemistry might have been the real gatekeepers for major evolutionary leaps. The slow decay of these two compounds shapes the whole trajectory.
It shows how interconnected the geochemistry and the biology were. Tiny chemical shifts dictating the pace of planetary evolution.
And this has implications beyond just Earth's history, right? The researchers mention astrobiology.
Absolutely. Understanding how our planet became oxygen-rich is crucial for knowing what to look for elsewhere. Dr. Ratnayak explicitly said this provides a new framework for the sample analysis strategies for future Mars sample return missions.
How so? What's the connection?
Well, if we find signs of past or present microbial life on Mars, say,
Goal.
right, we also need to understand the chemical context. Could Mars have had its own chemical inhibitors that prevented oxygen from building up, even if life was trying?
Ah, I see. So just finding biosignatures, signs of life, might not be enough to understand a planet's potential habitability for complex life.
Exactly. As the study puts it, understanding Earth's oxygenation sheds light upon the biosignature detection in other planets. It highlights this interplay between the inorganic chemistry, the rocks, the water, the trace elements, and the organic compounds in life itself.
So if we detect oxygen on an exoplanet someday,
Which would be incredibly exciting.
we shouldn't automatically assume Earth 2.0 with complex life. We also need to consider what else might be in that atmosphere or ocean chemistry.
Precisely. Are there high levels of nickel or some other element that acts similarly? Could there be chemical breaks applied, even if simple life is present and photosynthesizing?
It adds another layer of complexity to the search for life.
It really does.
So, to sum up this deep dive, 1 billion years of waiting for Earth to take a deep breath, And the answer might not have been some grand geological event, but the slow, patient removal of two chemical gatekeepers, nickel and urea.
Yeah, the quiet decay of inhibitors finally letting life off the leash. It makes you realize habitability isn't just about having the right ingredients, like water and energy in basic life.
It's also about not having the wrong ingredients in prohibitive amounts.
Exactly. The absence of certain roadblocks can be just as important as the presence of building blocks.
Which really leads to a fascinating final thought for you to ponder. If Earth's oxygenation was held back for so long by trace chemicals, things like nickel and urea,
Things we wouldn't normally consider major players in habitability.
does that mean finding signs of basic, maybe photosynthesizing life on another planet is only step one? Before we get truly excited about the potential for complex life there, do we also need to confirm that planet lacks its own set of invisible chemical inhibitors?
Could a planet be teeming with microbes but permanently stuck in a low oxygen state because of its specific geochemistry? Inhibitors that Earth eventually overcame, but another world might not.
It suggests the path to complex life might be even trickier, even more contingent on specific chemical pathways than we already thought. Something to definitely keep in mind as we continue looking out there.